All right, our FBD KD bonanza will begin with several pictures that we're going to draw. We'll start with a question that we had looked at in class. We'll make sure everybody's on the same page here. So we're told that we have a velocity of a jet, which is a constant. That obviously means that the v dot is equal to 0. And as we start heading towards drawing an FBD KD, we're going to do it at A, B, and C. And so let's take a look at the pilot. And so we'll draw a little picture of him sitting in his seat right there. So that's the FBD side, KD side. Oops, right there, sitting in his seat. And so on this side, we've obviously got the weight. We've got a normal force from the bottom of the seat and a normal force from the back of the seat on the right hand side. So if we go up and look at our picture here at point A, we have just entered into a half loop. So what we're going to do is use normal tangential. So the tangential, again, is tangential to the path, and normal is towards the middle of the circle. And we have two accelerations over here. I'd have a mass times a tangential, and then mass times a normal. We would know that the mass and the tangential is going to be v dot, which we already know because of constant velocity. V dot's equal to 0. And in the vertical direction, we've got that velocity squared over rho, which in this case is just r. So I'll just change that to an r right there. All right, so that's at point A. And again, of course, we would put our coordinate system on right there. So we'll go down and do now at point B. So now we're on a vertical plane here. So the pilot is now sitting like this, sitting on his back, or her. And we've got, again, acting the weight. I've got the normal force from the back of the seat. I've got the possibility of a normal force from the bottom of the seat. And over on this side, I've got a normal acceleration, which would be v squared over r. And again, if we go look again at point B, we've got the tangential up and the normal towards the middle of the circle. So there would be our coordinates at B. Go ahead and look at C. We end up with a pilot that is upside down. It's not the best picture. Not the best picture, but I think you get the idea. Up at point C, the tangential direction would be to the left, and the normal direction, again, would still be towards the center of the circle. So again, notice in all three of these positions, we're using a normal tangential, and the orientation of those directions has changed. And so there we've got a weight. We've got the possibility of a normal force in both directions. And acceleration-wise, we only have a centripetal acceleration, which would be mv squared over r. So again, we have no tangential acceleration at any point because v dot's equal to 0. We only have a normal acceleration. Now we've got another one here with a sphere that is revolving at a constant speed v. So we would say again, velocity is a constant, so we know that v dot is equal to 0. And again, that's independent of any coordinate system we may choose to use. And so what we will end up doing, it doesn't tell us which direction it's revolving. Let's just say it's going in that direction, theta dot or omega, right, with an angular velocity. And so that would put, so I'm going to draw this, that would put my normal direction there. That would put my tangential kind of going off in that direction. And then I would have a z direction going right there. And so if we draw the FBD KD. I'm going to use those same coordinates right here. I'm going to call that the normal. I've got the Z direction, right? And this tangential is sort of going off in that direction. And so the forces that I have, I've got, never forget the weight. I've got two tensions. I've got a tension that I'll call A. I've got a tension that's going up to point B. And I've got two different angles on there. That would be Pt1, and that would be Pt2. And from an acceleration point of view, I have an acceleration in the normal direction, mv squared over, in the picture right there, it's r. I have no tangential acceleration because v dot's equal to 0. And it says it's moving in a horizontal circle. So I've got no movement in the z direction, therefore no velocity or acceleration. All right, we've got a collar of mass m. That collar is sitting right there. In the picture, it's attached to a spring and slides without friction. All right, so we've got no friction. Along a circular rod in a vertical plane, the spring has an undeformed length of 5 inches with the spring constant K, which I'll just kind of put right there. Knowing that the collar has speed V at point B down here, we're going to go ahead and draw the FBD KD. So I'm going to go ahead and draw it nice and big right here. And down at B, right, I've got a collar that is again on a circular path. So down here, I'm going to put the tangential in the direction of the velocity. I'm going to put the normal towards the center of the circle. So there's my coordinate system. I've got force-wise over here on the FBD set, I've got a weight. Right? I've got a normal force, which is acting from the rod. You know, let me move that back just a second. Put the weight up here, that'll look better. Put the normal force right there. I've got no force of friction to account for. And then all the way down here, I've got the spring, the force, which will be going off at an angle, which we'll find in just a moment. And I know that the force in the spring is going to be equal to K times the stretch. So we'll just go ahead and keep that in mind here. Over on the kinetic side of this diagram, I've got mass times a normal acceleration, and I've got mass times a tangential acceleration. Now, unlike those previous problems, we're not told that the speed is constant. So I have no idea if the acceleration in the tangential direction is a constant. It's probably not. Right? I know it's going to be equal to v dot. And I know in the normal direction, the acceleration is just going to be v squared over rho, which in this case is 5 inches. So there's my accelerations. I've got now the force of a spring that I need to do a little geometry on. So if I look closer in there, I've got 7 inches, I've got 5 inches, and down at point B, then another 5 inches. So I've got a nice triangle, and so I can find the length is equal to 13, and therefore the stretch is going to be equal to 13 inches minus 5 inches, which is equal to 8 inches. So therefore the force in the spring is going to be equal to K times 8 inches, and it's going to be oriented at a 12/5 angle. So now a 130-pound wrecking ball, B, is attached to a 45-foot long steel cable and swings in a vertical arc shown. And so what we're going to do is just draw the FBD KD at 2 places, at C, which is up on the left side of the arc, and then D, which is all the way down at the bottom. And so we'll start here at C. And so I'm just going to draw two big circles over on the FBD side. I've got the tension in the cable. I've got the weight of that thing, right, which is going to be 130 pounds. And I know that that tension is at an angle of 20 degrees. And I'm going to put on there, use normal and tangential. I've got circular motion. So I'm going to go ahead and put tangent in that direction. I'm going to put normal again towards the middle of the circle. So there's my tangential, there's my normal direction. And so I've also got now back here, I've got a mass times v squared over 45 feet. And I've got a mass times tangential acceleration. And now we start applying a little bit of insight here. Up at point C, we're at the highest point on the arc. So at point C, this is a turnaround point, so I would know that the velocity is equal to 0. So that means that that term goes away. And so my unknowns that are left that I can solve for the tension, and I can solve for the tangential acceleration. So let's go ahead and look down now at point D. We've now got this ball which now has a tension force straight up and down. There's the weight equal to the 130 pounds. Now I've got at D, I'm going to go ahead and put the tangential direction in the direction of the velocity. The normal is going to be going towards the middle of the circle. And now over here I've got mass tangential, and I'm just going to go mass times velocity squared over 45 feet. Now down at point D, I certainly don't, should probably have a good intuition that the velocity is definitely not equal to 0. It's going to be at a maximum. But as we kind of see here, we've got the ability, if we go ahead and sum forces in the tangential direction, we would actually find that A tangent equals 0, or that V dot equals 0. So as we kind of look at what our unknowns are, we'd have an unknown tension, we'd have an unknown velocity, and two equations, not two unknowns, because we already used one of the equations to solve for AT. So this is going to require some kinematics. And so using some kinematics, we'd be able to use an expression that looked like A ds v dv, and we would end up integrating from the velocity at point C to the velocity at point D. Over here we would integrate from SC, to SD. So I have a couple of examples where we'll end up doing that, but you would need, the bottom line is you've got 3 unknowns and 2 equations, so we're going to need another kinematic equation here